All right, everybody, this is Mr. Mott again. This is the last video in our three-part series of explaining inter versus intramolecular bonds. All right. So looking at our example, our first example here, we notice that all of our bonds are going to be the same. So the bonds, again, are represented by these lines. These bonds represent forces of attraction between the carbon and hydrogen, and those are made of electrons. And so in all of our, each type of bond that we have in CH4 there are carbon-hydrogen bonds. The element with the stronger bond, we need to look on our periodic table. And when you do, you're going to notice that the carbon is further to the right and it's more electronegative. So carbon has the stronger electronegativity. And because these are both nonmetals but they're different, that means that we are going to have partial charges. So carbon being a little bit more electronegative is going to give a partial negative. Hydrogen is going to be a partial positive then by default. Now all of these bonds are the same, so we can put partial positives on the hydrogens for all of them. All the bonds are the same. In terms of classifying the molecule, we want to look for is our molecule polar or nonpolar? We're not dealing with ionic because ionic is when you have a metal versus and a nonmetal. Here, we are going to look to see, is there one side of our molecule which is more positive and the other side being more negative? Well, we don't have that the case. So if we look at the top and the bottom, the top is more positive, here's more positive. That is not a pole. If we look at this vertically, and we look at the left side is more positive, the right side is more positive, that is not a pole either. So there are no poles no matter how we look at this. So that means our molecule is going to be nonpolar. Okay. If we had another one of these molecules that wanted to bond next to it, then what you would have is that you would have positives next to positives. And so anytime that you have, and that would just be like what we had with hexane. So basically this compound that we just looked at is a mini version of hexanes. It's carbons with hydrogens all around. And we're going to have the same intermolecular bond that we had before, because this bond that is between the hexane, positive next to positive, is very weak, and that's going to be a London dispersion bond. All right? So anytime that you have nonpolar molecules bonded with itself, then you're going to have London dispersion bonds. All right. Next example is very similar, except for we notice that we have a fluorine down here. So what we can immediately do, so we have carbon to hydrogen bonds, and we have carbon to fluorine bonds. Between carbon and hydrogen, carbon is more electronegative, so we put partial positives on the less electronegative hydrogen. But between the carbon and fluorine, look in our periodic table, fluorine is more electronegative. It's our most electronegative element. It's further to the right and all the way up on our periodic table. So fluorine is going to have a partial negative here. So between which one has the stronger electronegativity, between the carbon-hydrogen bond, I would say carbon. In between the carbon-fluorine bond, I would say fluorine. So it's a little bit different case than we have here. We're still going to have the partial charges like we said because we're dealing with nonmetals that are bonding and they're different from each other. And this molecule, because the top part of it is more positive, the bottom part is more negative, that means that we're going to classify it as being polar. All right, it has a pole, it has opposite sides. The top has an opposite charge than the bottom, so therefore it's polar. When we have two polar bonds, we're going to have a dipole-dipole interaction, but what we have to think about is do we have one of our special dipole-dipoles, which is a hydrogen bond? So if we were to draw another molecule like this next to it, the molecule would turn itself in space so that one of our positive hydrogens, our partially positive hydrogens, is in close proximity to the negatively charged fluorine. That positive negative would create that bond. And so since you have a hydrogen bonded to a fluorine, that is a hydrogen bond. Okay? And again, this is the bond that is between them. And hydrogen bonds can, again, they can exist between hydrogen from one molecule and fluorine of another, or hydrogen to oxygen, or hydrogen to nitrogen. So another way of thinking about it is that if our molecule contains hydrogen and any one of these, and then it's going to bond with another molecule of itself, it'll exhibit hydrogen bonding. All right. Looking at our next example, oxygen to oxygen. So the oxygens are the only ones in the bond. We could say that we must have to say that the oxygen is more electronegative. It's the only one there. But what you have is that you have two elements with the same electronegativity, and when they start to pull on the electrons, they're going to pull on them equally. So that's going to result in no charges. Okay, so I'm not even going to have to draw anything on there. If there are no charges, it's got to be nonpolar. And if an oxygen with no charges bonds with another oxygen molecule, two nonpolars, that's going to be a London dispersion bond. Okay, and again, when we say bond with itself, this is an intermolecular bond, and that's what we have with London dispersion. All right. When we talk about intermolecular bonds again, these tell us a lot about states of matter, for instance. Oxygen under normal temperature and pressure is a gas. That makes sense because the bonds that are between this oxygen and other oxygens are going to be very weak, and that's what we figured out here. All right. Let's look at our next molecule here, BF3. So we have B to F bonds. From our example before, the element with the stronger, or the atom with the stronger electronegativity, fluorine, so it's going to have a partial negative. Oops. And boron a partial positive. Now, in terms of, so we have two nonmetals that are different, so that we're going to have partial charges. Looking at this molecule, all sides of our molecule are partially negative. What that means is that no matter how we look at this in terms of symmetry, all sides are going to be negative. The left side is more negative, this side is negative. So that is not a pole. If we were to look at this in terms of this line of symmetry, well, this side is more negative, the right side is more negative. So all ways that we can look at this molecule are going to have negatives all around. And another way of thinking about something that is nonpolar is that it's going to have an even charge distribution. All the charges on the outside are going to be the same. So that's another way of looking at or thinking about something that's nonpolar. All right. If it's nonpolar, again, bonding with itself, London dispersion bonds. All right. Next one we have elements in our bond are between oxygen and sulfur. On our periodic table, oxygen is actually above sulfur. If we find them, we have oxygen and sulfur. So our rule is that as you go up and to the right, it's more electronegative. So oxygen is more electronegative based upon that. They're both nonmetals, so but they're different. So we have partial charges. The oxygen is more electronegative, so it gets the partial negative. Sulfur is partially positive. We can look at this and say, well, the top part is more positive, the bottom part is more negative. So that means that we're going to have a polar molecule. So this polar molecule does not have hydrogen in it, so this must just be regular dipole bonds. All right. Lastly, we're going to look at CO2 carbon dioxide. We have carbon to oxygen bonds. Oxygen is further to the right on our periodic table. In the row, it goes like carbon, and then nitrogen, and then oxygen on the periodic table. Oxygen is further to the right. So that's going to be the more electronegative element. We're going to have partial charges because our nonmetals are different from each other. Oxygen being more electronegative gets the partial negative, carbon being partial positive. Now, based on the symmetry, we can look at, again, like which we always do, the left side looks like the right side in terms of charges, partial negative, so that is not a pole. If we look at it horizontally, it's the same idea. This is a linear molecule, so that doesn't really change anything. So there are no poles on this molecule, therefore that it's nonpolar. All right, so a nonpolar molecule, and therefore we have London dispersion bonds. These last two examples are really to illustrate how shape impacts the polarity of a molecule. The SO2 in nature is a bent molecule. Carbon dioxide is linear, even though they really have the same sort of charge distribution, but because the shape is different, the polarity is different. All right, hopefully that helps understand bonding, and thanks for watching. Bye-bye.